Right. So welcome to today's STEMS webinar. So we are very happy to welcome Maximilian Dax as our webinar speaker today. So Max is currently a principal investigator at the ELLIS Institute in Tübingen in Germany, as well as at the Max Planck Institute for Intelligent Systems. There he leads a research group for science and probabilistic intelligence. Before he joined his current positions, he obtained a PhD also from MBI for Intelligent Systems and the University of Tübingen. He also spent some time at ETH Zurich and Google Research. So his research focuses on probabilistic machine learning and its applications in science, especially in physical science. And he's especially well known for his work on simulation-based inference for gravitational wave observations. He has, for example, led the development of the DINGO software framework, which stands for Deep Inference for Gravitational Wave Observations. And that is what we will be hearing much more about during the talk today. So his title is Real-Time Gravitational Wave Inference with Probabilistic Machine Learning. So Max, please take it away.
Yeah, thanks for the very kind introduction, Mikhail. Thanks for having me. I'm excited to be here. It's a bit late for me, so I do my best to give a coherent talk. If anything is unclear in the talk, um, feel free to interrupt. So as Mikhail mentioned, I'll be talking about our line of work in gravitational wave inference with machine learning. And I want to start by motivating the field of gravitational wave astronomy by highlighting some of the discoveries that we had in this field in the past decade. So maybe most famously in 2015, through gravitational waves, for the first time ever, we could observe a merger of two black holes. So that was the Nobel Prize winning detection in 2015. Through gravitational waves, we know that some of the heavy elements we have here on Earth, such as gold or platinum, that they most likely were created in neutron star mergers. We can use gravitational waves to estimate the expansion rate of the universe. We can use it to test matter under extreme conditions or to investigate some of the fundamental concepts in physics, such as, for example, Lorentz invariance. Now, what all of these discoveries have in common, while they span multiple different physical disciplines, they all rely on a data analysis step called gravitational wave inference or parameter estimation, which is the kind of data analysis step that we are aiming to address in our work through machine learning. So since the first discovery back in 2015, the LIGO-Virgo-Cagra collaboration have detected several hundred gravitational wave events. So I think back 1 year ago, it was at around 300, maybe 100 or so events have been detected in the meantime. And all of these events are either one of the following three sources. So either the source is a merger of two black holes, so a binary black hole merger, a merger of a neutron star and a black hole, so neutron star NSBH, or a merger of two neutron stars, so a BNS. And following a detection for each of those events, gravitational wave data analysis aims to characterize the astrophysical source based on the data. And this is the step called gravitational wave inference. And by characterizing the source systems, I specifically mean estimating parameters such as the component masses of the two black holes or neutron stars, the spins, and the location and orientation of the system. So this data analysis step can be done classically. So what I'm about to show you how we can do this with machine learning is not per se a completely new thing. But the issue is that some of these more conventional methods of doing gravitational wave parameter estimation, that they are either too fast or either too slow or too expensive to fully make use of the data that we expect in the next decades. And this has mostly two considerations. First, efficiency, and second, the speed consideration. And from the point of view of efficiency, the main problem that we're facing in the next decade or so is that with the new detectors, such as, for example, Einstein Telescope or LISA, we will have a data influx that's around 1,000 times higher than what we're currently measuring in terms of event rates. So we're already struggling keeping up with data analysis in terms of computational cost, but in the future, this problem will be amplified by orders of magnitude. And the second reason we need accelerated methods is that in some cases it's not just about the efficiency, but we also need really fast inference results in order to inform, for example, searches for electromagnetic counterparts. So I now want to explain what I mean by gravitational wave inference. So at its core, it comes down to comparing theoretical models to the data we observe. So if you think about a black hole merger, for example, this would be an astrophysical system of two black holes that spiral around each other and merge into a single and more massive black holes. And this would happen typically millions of light years away from Earth. This process then emits gravitational waves, which are small deformations in space-time that travel and propagate through space and can ultimately be measured here on Earth, for example, in the LBK interferometers. And the data that we measure from these events is then time series measurement of the corresponding gravitational wave, which is indicated, for example, with this example time series from 150914 in the center of the slide. Now, extracting the source information, as I mentioned, basically comes down to comparing theoretical models to our data. And the reason is that depending on what the astrophysical source system looks like, the shape of the gravitational wave is expected to change. So in other words, from the shape of the gravitational wave, we can make statements, we can infer properties of the astrophysical source. And I'm just qualitatively illustrating that with the simulation in this slide here, where we see that if I change the masses in a fictional black hole system, I can change the shape of the gravitational wave. And if I find the right combination of black hole masses, I can make the simulation line up with the data, which tells me intuitively that I found a plausible source system that could have given rise to the data. And doing that in a more systematic and quantitative way, that is the central task in gravitational wave data analysis. Now, from a data analysis perspective, this inference task is an inverse problem. Where we have two data domains. So on the one hand, we have our physical system, which is described by a set of parameters theta. So in our case, the physical system would be a black hole merger, and theta is a set of 15 parameters, typically containing, as I mentioned, the black hole masses, spins, location, and orientation of the system. And the second domain is the measurement. So the measured data, which in our case is a time series data, and it's maybe around 100,000 dimensional. And typically, the models that we have to connect these two domains, they are defined in the forward direction, so in the causal direction in which physics is actually happening. So they map from the physical system for measured data. Or in other words, if I have a specific black hole system, I can simulate a corresponding measurement. Or I can, in other words, more technically, I can sample from a likelihood. I can sample some data, so an observation, conditional on the black hole system. But what's interesting in practice is, of course, the inverse direction. So going from the measured data and mapping back to the physical system in order to characterize it. And in astrophysics, typically, the inverse direction is very often done in a Bayesian paradigm. So we're interested in inferring the Bayesian posterior, which is a probability distribution in the space of theta. So in our case, in the 15-dimensional space, conditional on the gravitational wave measurement. So the Bayesian posterior then summarizes kind of the knowledge that we have about the astrophysical source after seeing the data D, and it is defined by the likelihood, which is implicitly defined by the forward model, and a prior belief we have about the parameters before making any observation. And the task in Bayesian inference is then to infer this Bayesian posterior distribution, which is, as I mentioned, a probability distribution. And since it's a probability distribution, it captures all of the desirable probabilistic properties that we may want from inference, such as, for example, uncertainties for individual parameters or correlations between different parameters. And sampling the Bayesian posterior is the ultimate goal here. So the reason is that probability distributions itself are very hard to work with. So it's probability distributions are high dimensional densities. And it's very hard to kind of visualize data for these, to marginalize over parameters, to compute expectation values. So what one instead typically wants to do is one wants to generate fair draw samples from the Bayesian posterior. And a sample literally just means generating a plausible set of parameters for theta. And this is generally a really tough question or a really tough task to sample such probability distributions. And in machine learning, the way this task is typically being addressed, or in many cases, is by training emulator neural networks for the corresponding probability distribution. So essentially what we want to do is we want to train a density estimation neural network, so a type of neural network that can parameterize a density in the space of theta. And we want to train this to match the Bayesian posterior. And after we've trained the neural network to indeed be a good approximation of the posterior, at inference time, we can simply provide the gravitational wave as input to the neural network and then sample from the neural network instead of sampling from the Bayesian posterior. So the neural network in the end is that an emulator or kind of a surrogate model for the Bayesian posterior that we can directly and very efficiently sample from. So at the highest level of abstraction, the setup looks as follows. So we have our gravitational wave, which is passed as input to a neural network. The neural network then performs some computation and predicts a set of black hole parameters theta, so basically 50 numbers. Now, as I motivated, this needs to be a probabilistic framework in order to capture the uncertainties and correlations and so on. So this can't just predict 50 numbers, so it can't just be a normal feed-forward neural network, but instead it needs to be a network that can sample different parameters. So every time I query the neural network, I get a different source system. So I get a different set of parameters theta. And then I can sample from the neural network many different times, and I can post-process the individual samples, for example, by making histograms, and ultimately, for example, create the corner plots as shown here on the right-hand side. Now, training such neural networks requires some training data, and the way this is typically generated in these simulation-based inference approaches is by creating a data set of samples from the joint distribution, so the distribution over black holes and gravitational waves, via first sampling from the prior. So we first sample a set of black hole parameters from the prior, and then sampling from the likelihood. So we simply, for each of the black hole mergers that we sampled from the prior, we generate one simulation using our forward model. And this then results in a large data set of black holes paired with corresponding simulations. And we then train the neural network to predict the conditional distribution. So using the samples from the joint distribution, we ask the neural network to predict the conditional distribution. So to predict black hole parameters conditional on gravitational wave measurements. And as I'll show in the next slides, this can simply be done by regressing on a negative log likelihood loss. And so I'll motivate the steps in more details in the next couple of slides. But I want to point out here an analogy to kind of mainstream AI research, because many of the models that we may be using on the site, so such as, for example, the text-to-image models in ChatGPT, are precisely such conditional generative models. So, for example, the text-to-image generative models in ChatGPT that takes as input a text prompt, such as a cold rainy night in Stoke, and then as output provide samples of images. They are, in a sense, mathematically solving basically the same task. So we generate lots of samples from a joint distribution over text prompts and images, and then we train a generative model to predict images based on text. So mathematically and in terms of the neural networks that we're using, it's very close to these technologies that are used in these very big modern AI models. So now I want to explain a bit in a bit more detail how precisely we do that. So as I mentioned in the previous slides, we can't simply use feed-forward neural networks because we need to parameterize probability distributions. So those are not simply point estimates for black hole parameters, but instead we need neural networks that are capable of parameterizing probability distributions. And for that, we use a technique that I guess many of you would have heard of or probably even used yourself, specifically normalizing flows. So a normalizing flow is a way to parameterize the probability distributions by starting from a simple distribution in the space of the same dimension. So typically the simplest distribution one can write down is just a zero mean unit variance Gaussian, and in our case that Gaussian would be a 15-dimensional Gaussian. And then one defines a transformation that transforms this base distribution, so this Gaussian, into a more complicated distribution that then is the density estimate by the neural network. This transformation FD is typically implemented with some neural network that has certain properties in order to make everything tractable. And with that definition, one can both sample from the distribution Q, and evaluate the density efficiently. So sampling from the distribution simply requires sampling from the base distribution. So we sample from the Gaussian and then applying the transformation F to map the sample from the Gaussian into a sample from Q. And density evaluations basically require the inverse direction. So to evaluate the density at a certain parameter theta, we apply the inverse transformation f to the -1 in order to map back into the space of the Gaussian, evaluate the Gaussian density there, and then have a contribution from the Jacobian determinant due to the change of variable formulas for probability distributions. So with that implementation, we can basically parameterize the probability distribution that's very expressive, that can be sampled, and we can evaluate the density at the same time. Now, in practice, it is a bit difficult to set up these distributions, these neural networks that parameterize the transformation f, since they need to have certain properties in order to allow for efficient sampling and density evaluation. And so what's usually being done is to compose the transformation f by a series of smaller and simpler transformations, all of which are parameterized with neural networks. And the key result in the normalizing flow literature is that by stacking enough of these simple transformations, one can make the normalizing flows arbitrarily expressive, so they can really estimate any density. Okay, so now a normalizing flow gives us a very powerful way of parameterizing densities, but we still need to train the normalizing flow to fit it to actually match our posterior distribution. And we do that with a technique called neural posterior estimation, which is based on the minimization of the KL divergence. So the KL divergence is, of course, a measure of how different two distributions are from each other. And the KL divergence between the Bayesian posterior P and our estimate Q is simply defined as the integral over P log P over Q. Now, this is the KL divergence for fixed data. So in our case, for a fixed gravitational wave, for example. So in order to make this work for all possible data, we need to average over the data D. So we do this by simply integrating over D, weighting with the so-called Bayesian evidence P of D. Then we do some very simple steps. We replace the Bayesian posterior with Bayes through Bayes theorem with the prior and the likelihood. We realize that the last term here in the log, that this is simply a constant with respect to Q. So this term doesn't contain doesn't have any contribution from the density estimator, and the density estimator is the only quantity that we have control over, the only quantity that we want to train. So we can simply drop this constant. Then we can rewrite the integration, do a Monte Carlo approximation of the integral, and in the end we find that the KL divergence between P and Q can simply be approximated by taking through Monte Carlo approximations of samples from the prior and corresponding samples from the likelihood, with the integrand simply being minus log Q of theta given D. And that's obviously up to the irrelevant constant from above. So in other words, we can train our normalizing flow with a data set of samples from the joint distribution generated via sampling black hole parameters from the prior and corresponding gravitational wave simulations from the likelihood. So we use that to generate a data set, and then we simply minimize the log likelihood of Q across this data set. And this then should minimize the KL divergence between the normalizing flow estimate and the underlying Bayesian posterior. And the key result is that since we minimize the KL divergence and normalizing flows can be made arbitrarily expressive, we will asymptotically perfectly recover the Bayesian posterior. So that is, of course, not a practical statement, but an asymptotic statement, because in practice we won't have perfect optimization to the global optimum, and we won't have arbitrarily large neural networks. But asymptotically, what we're doing should converge to the true underlying posterior. So this is the general simulation-based inference setup. And while I've motivated it with gravitational waves, everything that I've talked about so far is basically just simulation-based inference, right? This is what's being used in other fields. And now I want to talk about what exactly we modified in order to make this work for gravitational waves. So just a reminder, the basic setup looks as follows. We have our gravitational wave data as input to a neural network, which then predicts the Bayesian posterior. And over the over the years, we've looked into into several components in order to make this framework work in gravitational waves. Because in practice, it's obviously not as easy as just using this neural network and everything works out of the box. So I want to highlight some of the things that we did over the years in order to actually make it work. So one of the things that we looked at in the very beginning is how we can adapt our neural networks to changing detector noise properties. We then looked into how we can integrate certain known properties of the gravitational wave models, in particular symmetries that relate the data to the black hole parameters. We came up with a method that guarantees accurate inference. We looked into neural network architectures, or rather density estimation methods that improve the expressivity of our density estimators. We came up with methods to handle extremely high dimensional data that may arise for some kinds of gravitational wave events, and with a method to handle missing data that may be, for example, due to contaminated segments of detector noise, of detector strain. And in the rest of the talk, I want to highlight some of these components, starting with adaptation to changing detector noise properties. So I motivated in the beginning that gravitational wave inference really is an inverse problem. So we're trying to invert a forward model. So of course, the inference problem is therefore defined by the forward model. And I want to motivate what model we use in gravitational wave inference. So as a reminder, the forward model is, of course, the simulator that takes as input black hole parameters and as output provides a simulated gravitational wave. And in gravitational wave astronomy, we generally assume that our observations consist of two components. So we have a signal component and we have a detector noise component. And then the signal is simply the sum of these two components. And for the signal, we generally assume, or we generally have deterministic waveform models that are inspired by general relativity. So those can be phenomenological models or effective one-body models. But in the end, all the models that are used in gravitational wave astronomy are in a sense deterministic models that compute a time or a frequency series based on the black hole parameters or on the source parameters theta. The detector noise, on the other hand, is of course stochastic. So we generally assume that the detector noise is Gaussian and stationary. And that these assumptions leave a set of three parameters, namely the so-called detector noise power spectral density, which basically quantifies the detector noise level as a function of frequency. So this is what you see here, and this is really a property of the detector. So the more sensitive the detector is, the lower this spectrum. So that just means that we have a better that we can better resolve the signals. And intuitively, the detector noise power spectral density is really just the detector noise amplitude over different frequencies. And you can see, for example, here at 60 hertz, you can see a spectral line. So the detector has a lot of noise at 60 hertz, and this is just because of the North American power grid, which operates at precisely this frequency. So those are the two components. We have the general relativity model, which is a deterministic model, and we have our detector noise model, which is stochastic, but we can control it. Namely, we know what model assumptions we make, but it has these three parameters of the detector noise model. So the basic setup for gravitational wave inference looks as follows. So we have our gravitational wave data D that we pass through an embedding network in order to compress it down to a lower dimensional estimate, and then we use that to condition the normalizing flow that ultimately estimates the Bayesian posterior. But as I've just mentioned, the detector noise spectrum actually enters the likelihood. So this is relevant in order to do inference. However, this spectrum is not fixed. It is a detector noise property that varies over time. So throughout the course of an observing run, this spectrum may drift. And we need to account for this in order to have accurate inference, because this enters our assumptions about the data generating process. And the way we integrate this is by simply augmenting the simulation-based inference setup. So instead of just sampling parameters from the prior during training, we also sample detector noise spectra from some empiric distribution over over the detector noise levels, and then we additionally condition the neural network on the detector noise that the data was being generated with. So the detector noise spectrum is fed along with the data to the embedding network in order to condition the normalizing flow. And what this does is it makes the NPE model tunable to varying detector noise levels. So we can instantly tune to a changing detector noise level by simply providing that spectrum to the normalizing flow in order to contextualize the data. So what this allows us to do is to basically use a single inference network for an entire observing run despite drifting detector noise. So in this first paper from 2021, we trained one of these NPE models and showed that basically over the entire course of an observing run for any event at any time, we could basically replicate the MCMC proposal with our neural network. So since this is a so-called amortized approach, so we train once, and then once we have trained, we can very cheaply analyze an arbitrary amount of events. This is of course much faster than MCMC because we have front-loaded the computation, so the computation was done ahead of time. So our model performs inference in only seconds, whereas MCMC took days for inference. And so I don't want to go into the detail of the corner plot here. Basically, it shows one-dimensional marginals on the diagonal and two-dimensional correlations in the lower triangle. But the key point here is that the blue result is very close to the orange result, so both samplers agree. And as mentioned in the intro, the method we dubbed that DINGO, which stands for Deep Inference for Gravitational Wave Observations. Okay, so now the results on the previous slides, they were actually not done with vanilla NPE plus this noise conditioning, but instead we needed one important ingredient in order to actually get good performance, and that is thinking about the symmetries that we have in gravitational wave inference in order to boost performance. And I want to motivate this with the following example. So gravitational wave data, I mentioned is originally available as time series data, but we typically look at it in frequency domain because this is where the noise covariance matrix is diagonal. So when we work with it, it's really a frequency series. So imagine we have some measurements, some frequency series as shown here in black, and some corresponding posterior. So I here show the posterior over the two black hole masses M1 and M2 and over the time of the merger. So basically the estimated time at which the gravitational wave from the merger arrives in geocenter. Now, we can apply a time shift to frequency domain data. So this is simply a local phase shift. So if we multiply the data with e to the minus 2 pi I f times delta t, this is simply a time shift in Fourier domain. So we know that the resulting posterior should be the exact same thing. So the so the component masses shouldn't change just because we time shifted the data, except for the time of the merger, which should be time shifted by exactly delta t. And this is of course a symmetry of the whole data analysis problem. So the posterior is invariant under joint application of the transformation in theta. So basically adding plus delta t to the parameters and the corresponding transformation on the data. So namely the local phase shift. So this is a symmetry that NPE would typically learn from simulation data. So this symmetry is captured in the simulation data. But it's of course wasteful if we know that symmetry exists. It is wasteful for the neural network to learn this simply based on data. So this will result in substantially worse performance because the neural network needs to devote substantial capacity and training budget to learn the symmetry that we had known in advance. So what we back then tried to do is to instead enforce such symmetries by construction and free up neural network capacities in order to learn other patterns that are maybe harder to integrate by hand. And the method that we came up with is called group equivariant NPE or GNPE. And the whole idea is to integrate symmetries via data standardization. So that is something that is extremely complicated to explain. So that would probably require an entire talk on its own. But I'm going to try to give the kind of the one page or the one slide summary of this. So imagine if we knew the time of coalescence, so if we knew the merger time of the gravitational wave event, then we could simply subtract that time. So we could time shift the data by minus that time in order to align the data, and we would always ever analyze data with a merger time of 0. So we would only ever analyze untime shifted gravitational waves. But the problem is that this time parameter is unknown at inference time. So it's one of the parameters that we instead want to infer. So we can't simply align and standardize the data in that way. And the method that we came up with to nevertheless do this in an iterative way is the following. So for every symmetry parameter, so in this case t, we introduce what we call a proxy. So this is called t hat in this case. And we define a conditional distribution over the proxy through some kernel that is centered around 0. We then sample at inference, we sample from the joint distribution over theta and t hat. So t hat is a parameter that we've defined, so we can simply analyze the posterior and the joint space over this artificial parameter t hat additionally. And in the end, after we sampled in the joint space, we simply marginalize over t hat and we're left with samples from the parameter theta. And the way this works in practice, so the way we sample in the joint space is through Gibbs sampling. So essentially, Gibbs sampling tells us that we can iteratively sample t hat conditional on theta, and always the data d as well, and theta conditional on t hat. And if we iteratively sample these steps, we ultimately converge to samples from the joint distribution as we want. Now, the key here is that via this iterative procedure, we can actually simplify our data representations. So the first step in Gibbs sampling, so sampling t hat conditional on d and theta, this is trivial. So this there we just have our transition kernel that we defined above here. So we can always sample t hat based on t without even looking at the data. So the complicated step is really how can we sample theta conditional on t hat and also conditional on our data. And this is now where we can make use of the fact that we condition on t hat. So our neural net, our NPE network knows about the time proxy in our case. And this means that we can apply any invertible transformation to d that also depends on t hat. In particular, we can time shift by minus t hat in order to standardize the data. So what this means is that the data that the neural network sees ultimately has a time shift of at most plus minus 1 millisecond in our case, because that's what we chose the kernel to be, instead of the prior, which is around 100 times larger. So this is kind of the summary of this method. In practice, it's of course more general than just applying to time shifts. And I've left out some details here, but this is the rough intuition. So we introduce for each symmetry, we introduce an additional nuisance parameter in order to capture the symmetry, and then we extend the parameter space, sample in the extended parameter space, and in the end we discard the nuisance parameter, marginalize over it, and we are left with samples from the distribution that we want. So I want to show what effect that has in practice. So these two plots show again two posteriors for two gravitational wave events. And now the baseline result generated with MCMC is shown in black here, and the NPE result is shown in blue. And we see that the NPE result is maybe an okay approximation of the posterior, but there are clear deviations. And if I take the same NPE network, so same hyperparameter, same training budget, same everything, and I only turn on the symmetry component, we now get the orange result, which again is a perfect match almost for the black result. So integrating the symmetries really helped here. And I want to illustrate this further. So I mentioned that GNPE is this iterative method. So we're sampling between the nuisance parameters and the black hole parameters, and we do this iteratively. And I want to show how this converges, even if we deliberately initialize the sampler quite poorly, so with very bad nuisance parameters. So in blue, I'm again showing the MCMC result. So this is can be thought of as the ground truth posterior. And in orange, I'm showing the GNPE result and how it develops over iterations. And in this animation, I kind of chose the time resolution such that it matches the inference time on a back then I think it was a V100 GPU or an A100 GPU. So this is real time how the posterior converges to the actual MCMC result over the course of multiple iterations, even if the original initialization was quite poor. Okay, so that was the sectional symmetries. Now I want to talk about how we can actually verify the results. Because even if we integrate symmetries, neural networks are still a black box in the end, right? And we don't really know if the neural network hallucinated for a certain result or not. And if we want to trust our neural network results, we kind of need to be sure that that I don't know, maybe the paper we publish is at some point with a scientific discovery where the data analysis was done by machine learning. We need to be sure that the machine learning model didn't just hallucinate and that our results are actually scientifically valid. And what turned out to be the solution for us to that issue was by simply combining neural importance by simply combining NPE with very basic importance sampling. So the idea is the following. We have some underlying ground truth posterior, which is indicated here for this 1D distribution in blue. And we have our neural posterior estimation estimate, which is shown here in orange. And maybe the NPE result is not a perfect match for the distribution. Maybe we haven't trained for long enough. Maybe the neural network wasn't big enough. Maybe something went wrong during training. But now the idea is we don't say that the NPE result is the final result, but instead we say this is merely the proposal distribution that we're going to use to then importance sample to the exact likelihood, to the exact posterior. So importance sampling simply requires sampling from the proposal distribution, which we can because normalizing flows are easy to sample, and then reweighting the sample with a weight that is proportional to the ratio of the density in blue and the density in orange. So basically, in places where we find that the blue density is much larger than the orange density, we can simply downweight the corresponding sample. Whereas in places where the blue density is too small, so is smaller, so we oversample, we simply downweight the sample. So this is just basic importance sampling. It's very well understood, and we know that it's asymptotically exact. So if we sample with importance sampling, this is again this is kind of guaranteed to give us to sample from the Bayesian posterior or from the target distribution under certain conditions, obviously. What's super useful about this is that this comes with an independent performance metric. So we don't need to compare to ground truth posteriors in order to in order to understand how well we perform. So specifically based on the variance of the weights, we can compute a quantity called the sampling efficiency, which tells us how well we did. So obviously, if the NPE proposal was a perfect match for the blue target distribution, then all of the weights would be constant, and we would have basically zero variance in the weights, and the sampling efficiency would be at 100%. But if there's a difference between the proposal distribution and the target, then we will get smaller sampling efficiencies, and we will know based on the sampling efficiency how well we did. What we also get for free from importance sampling is an estimate of the Bayesian evidence. So we basically get the normalization of the posterior simply based on the importance weights that we compute. And it also scales with 1 over square root of n. So if we need a more precise estimate of the Bayesian evidence, we can simply, at inference time, generate more samples from the Bayesian posterior, generate more importance samples, and we will automatically get a more accurate and more precise estimate of the Bayesian evidence. So what this allowed us to do is to analyze very large catalogs without needing to run expensive MCMC methods. And it also allowed us to scale to more complicated simulators, where maybe even despite the methods that I've mentioned in the previous slide, maybe Dingo didn't perform perfectly accurate. And so an example of this is shown in this plot here, where again there are small deviations between the MCMC result and Dingo, but after importance sampling the Dingo result, we see that the deviations basically vanish, and that Dingo IS, so this importance sample result, basically matches the ground truth posterior again. So this allowed us to use to analyze a large gravitational wave catalog for very expensive forward simulators for which MCMC would have taken months per event without needing to actually run MCMC to verify that inference was indeed correct. We found that when inference did not work, so in some cases there Dingo failed to recover the correct posterior, but that then was flagged with very low sampling efficiencies. And we generally found that also the evidences we generate, that they are consistent with nested sampling, so which is usually the gold standard in order to compute the Bayesian evidence. But we found that with importance sampling, it's around 10 times more precise than the highest precise than the most precise estimates from nested sampling. So that's that was the section on the inference on the inference accuracy guarantees. So I'm kind of running out of time, so I'm gonna be a bit faster in the last couple of sections. So one of the more recent challenges was how we handle data when it becomes very high dimensional. And the motivation for this is a specific type of event, namely binary neutron star mergers. So we see in the distributions of events that we've encountered so far that most of the gravitational wave events are black hole mergers. So those are indicated by two blue dots, so two black holes merging into another blue dot. So two black holes merging into a bigger black hole. But there's also these two events here, and those are neutron star mergers. So neutron star mergers are basically the same thing, only now we have two neutron stars merging into either a neutron star or a black hole. And these are really exciting from a scientific point of view because neutron stars, in addition to gravitational waves, they also emit light. And if we can infer the position of the neutron star merger from the gravitational wave data, we can use that to basically point electromagnetic telescopes in the direction of the neutron star merger and potentially measure the light in addition to the gravitational waves. But this requires very fast gravitational wave data analysis since otherwise the electromagnetic counterpart is gone before we can actually measure it. So this is actually where the stakes are the highest. Neutron star mergers, this is where we actually also need inference speed. So so it was always clear when we started working on simulation-based inference for gravitational wave analysis that at some point we wanted to scale to neutron stars because this is where the scientific stakes are the highest. But the issue is this is also the most complicated problem because the data can get extremely high dimensional. And this is simply because the in-spiral of two neutron stars with much lower masses than black holes just takes far longer than a black hole merger. So we have far longer time series, which means that in a frequency series, we need a way higher resolution. And the data can get, for example, up to 10 million dimensional in certain detector setups that we considered. So we need some way of dealing with this super high dimensional data, and this is really the key to cracking binary neutron stars. And just to illustrate what high dimensional data means, so this here is a frequency series of a binary neutron star signal, of a simulated signal, and we see that it oscillates so fast in frequency domain that we need an extremely high resolution in order to capture it. Now, what we now you can compress this signal, namely with the following technique. So if you know a parameter which is called the chirp mass, which is basically a combination of the two neutron star chirp masses, we can infer the overall leading order evolution of the phase of coalescence, or not the phase of coalescence, but of the phase of the signal. So the gray signal is the real part of the detector noise of the detector strain shown for a simulated signal, and this oscillates extremely quickly. But if we factor out this leading order phase, we see that the signal oscillates much less, and we could have used a way smaller resolution in order to capture the signal. And then once we factored out the phase, we can simply average nearby frequency bins. So for example, in this little inset, you see I can probably average all of the frequency bins in this little range here because the signal has this, the signal won't change between those bins, but the noise will. So basically, we're trading a lot of bins with a bit of signal and a lot of noise for a single bin with the same signal content but less noise. So basically, we're not losing any information, but we're basically discarding a lot of the noise. And if we combine these two techniques, then we can compress the data without losing any information by a factor of 100 or so. And then we have a feasible problem again. Then we maybe have 100,000 dimensional data or so, which again is feasible to handle with the neural networks of the sizes that we can currently fit on a GPU. But the issue with that compression technique is that it depends on one of the parameters again that we in fact want to infer. So it is one of the parameters that is unknown prior to inference. And basically a major contribution of our paper on extension to binary neutron stars is to enable this compression despite not knowing the chirp mass. And this is based on the observation that the posterior over the chirp mass is extremely tightly constrained, but we don't know ahead of time where in the parameter space this will be. So basically, I'm going to skip over this since I'm running out of time. But basically, the technique we developed was to train a single neural network with multiple different priors that are and all of the priors that we train with are extremely tightly constrained, and we always compress the data with respect to the center of the prior, and therefore get really good compression by the factor of 100 or so that I motivated on the previous slide. So and also to relate this back to some of the earlier work, this kind of prior conditioning technique is basically the lightweight version of the GNPE technique that I introduced in one of the earlier slides. So this is really at the heart of Dingo when applied to BNS. So this compression technique is the most important component. Then we applied several other techniques to solve some of the practical problems when scaling to binary neutron stars. And the final result could then perform inference in only 1 second of inference time for binary neutron star systems. And this, as I mentioned, is particularly exciting because it can allow us to get very fast sky maps, so very fast localization for binary neutron star mergers in order to search in a more informed way for electromagnetic counterparts. And maybe one of the most exciting results is that for next generation detectors, we can do this pre-merger inference maybe 30 minutes before the merger. So half an hour before the merger, we will already know with relatively good precision where the gravitational waves are coming from and where we could look for the electromagnetic counterparts of the neutron star mergers, which could hopefully enable to measure the electromagnetic counterparts during during the time of the merger. Okay, so I'm going to skip over the last part and go straight to the conclusion. In this talk, I introduced Dingo, which is a framework for fast machine learning based inference of gravitational wave data. We have started using it for scientific discovery. So my colleague Niha, for example, has a paper on looking for eccentric black hole systems with Dingo. We are under review at the LVK for production use. So we're really trying to push this to be used by the community also, and hope that in the future this can give us some interesting science results beyond all the data analysis considerations that we've looked at so far. It's also gravitational wave inference in general is also a really exciting field to test and develop machine learning methods in general. So I've really enjoyed working in this, even just from the machine learning perspective. So irrespective of what you can do from what you can do with it from the scientific perspective, it's just a really exciting problem with basically endless problems that you can try to tackle. And if I had to kind of summarize the whole concept of it, the idea of amortized simulation-based inference in general, in most sciences, but in particular in gravitational wave analysis, is that through machine learning we can front load the computational cost of data analysis. So, for example, through extensive pre-training of our neural networks. And this then allows us at inference time to do very efficient inference for any number of events. So that's the general concept behind it. So there's many open questions, in particular in the context of next generation detectors, many problems we haven't solved yet. So there's at this point maybe more open questions than there were when we started 5 years ago, which is really exciting. So many things where machine learning can hopefully help the scientific community to kind of advance in their field. So I'm really looking forward to the next years and working on these problems. And that is the end of my talk. Big shout out to many great collaborators. And those are the publications that I mostly talked about. And I'm now happy to take questions.